Just a short video on an important safety trick if you are using 240 volt emergency lighting or property lighting. If, say, you're like me, you have a bunch of land and need to run lights all over the place, you can get away with much longer runs for a given load at 240 volts versus 120 volts on a given cable. Like, for example, all these lights here, even that 150 watt metal halide fixture, they are all running on almost 1,000 feet of extension cords, and 900 feet of that is 18 gauge. Yeah. However, using 240 volts presents a problem specifically here in 120 volt mains land. And that's because here the standard lamp base for 120 volts, for general lighting lamps at least, is medium screw base. What this means is that if you're using 240 volt lamps, which all of these lamps are, except that one is 235 volts, even though it says 230 to 240 volts, typically when you see a potential range, the actual design potential of the lamp is in the middle, so 235 volts. Also, yes, that is a Soviet-made Razno lamp, because of course I have some of those, because I'm special. But anyways, the problem with this is that if you have medium screw base fixtures, it's very easy, especially if you're supplying electricity to neighbors who aren't as technologically knowledgeable as you are, is, dude, the lamp died or the bulb died, because 95+% of people improperly call lamps light bulbs because they're idiots. Best case scenario is you stick a 120 volt lamp on 240 volts, is it'll burn out at most within a couple of minutes, more likely within a couple of seconds if it doesn't fail instantaneously. However, that's with incandescent and halogen lamps. Most LEDs, well, actually almost all LEDs nowadays that are 120 volts are 120 volt only, and all compact fluorescents that are 120 volts are 120 volts only. And LEDs and compact fluorescents, you shove too high a potential into them, they can explode and catch fire, which, especially in an emergency situation, is a very bad thing. Not that it's a good thing at the best of times. However, there's a way around this, and that is by using deliberately incompatible bases. There is, however, one that you specifically want to avoid. That is this, what the Brits call a small bayonet cap, what we would call an intermediate dual contact bayonet base. Because even though this particular lamp here is 230 volts, this base is very commonly used with indicator lamps and automotive and miniature lamps that are usually in the range of 6 to 28 volts or so. On 240 volts, those lamps will become grenades. So, especially if you've got 12 volt or 24 volt emergency lighting that uses this lamp base, you really want to steer clear of that particular base. There are two bases that are much better for this because they're very rare over here. And that is this, what the Brits call small Edison Screw. It's the European candelabra size. And much more common and wider range of lamps is available for it. Medium dual contact bayonet. Because I've got this Woolworths branded 100 watt lamp, even though it doesn't have any country of origin or manufacturer's mark, it is bloody high quality lamp, because if you look in there you see it has a Balatini fuse, and especially in 240 volts that's kind of bloody important, because 240 volt lamps, especially on a supply with a very low source impedance, can blow up, and that's why it's often recommended that those lamps are used in enclosed applications or enclosed fixtures. Although if you're running it on thousands of feet of extension cord, not really going to be that much of an issue. And of course you can also get compact fluorescent lamps like this. So another GLS lamp there, status, so it's from 2006, so it might be Eastern European, although it's probably Chinese. And that lamp, which was made in Hungary. I think in either Budapest or Nagykanizsa, which are the two Hungarian GE lampworks that I know of, although I know there are a couple of others. So it might have been made in one of them. And of course, this means that you can standardize on having medium dual contact bayonet for 240 volts, especially for lights that are going to neighbors. If it's stuff that you're going to be using, then screw base is an option. Just mark on the lamp holder, mark on the fixture, this is fed by 240 volts, only use 240 volt lamps, comma, you idiot. But yeah, stuff that's going to be going to neighbors, where other people have to change out lamps, use a type that they are not going to have access to 120 volt lamps that have that lamp base. Now, of course, if you are running a transformer on the other end of that system, because say it's the summer or late spring, early fall, and you don't have access to a ready supply of ice to keep refrigerators cold, and they have there's a step-down transformer on the load end to run 120 volt appliances, refrigerators, microwaves, etc., then yeah, you can use 120 volt lights. However, the thing is, then you've got the phantom loss of the phantom load of the transformer, because it's going to be using anywhere from like 10 or so all the way up to some cases close to 100 watts, and that's just watts. That's not even factoring in the power factor and reactive power loading. And of course, yes, that is a 115 volt lamp running on this transformer. It is a Osram made in the Shaw Lampworks in Oldham, which closed down in 2000. This particular lamp is May 1996. Now, of course, one issue you can have with very long extension cord runs is drop from surge loads. For example, right now I'm getting about 229.6 volts, and that's with 150 watt metal halide, 60 watt lamp there, that's a 14 watt compact fluorescent, 16 watt compact fluorescent, 25 watt yellow GLS, and that 60 watt GLS lamp over there. However, note the 1 kilowatt GLS lamp. Let's turn on max minimum. 3, 2, 1. Yeah. Dropped down to 133.6 volts when I turned that lamp on. And the reason for this, actually, let's see what we're at now. At 183 volts. Is because incandescent lamps, when off, have a resistance of anywhere from about 1/7 to 1/15 their operating resistance. So this lamp, which is a 250 volt 1 kilowatt lamp, has a nominal operating resistance of 62.5 ohms. When cold, it's more like 5 or 6. So, with these very long extension cord runs, that introduces a very considerable resistive line loss, because just these extension cords, the 18 gauge, 300 foot ones, have a resistance of about, I calculate out, it is like 4.5 ohms or something. So that means that between all these various extension cords, there's close to 14 ohms in series with all of this. And so, that lamp on, yeah, we're only getting 183 volts. Now, one thing this can also have an issue with is extinguishing fixtures that are HID, because this is a metal halide fixture, although it's wired for 240 volts. Interestingly enough, the lamp stayed lit, because I've done this experiment before and it's caused the fixture to extinguish. And of course the issue with HIDs, unless it's a hot restrike high pressure sodium lamp, which is one of the ones with the dual arc tubes, they go out almost immediately. And can take minutes to restrike. Now let's turn off the 1 kilowatt. And see there, we've recovered 233 volts. But yeah, that's a one thing you have to account for, especially if you're running motor loads. And say well pumps especially. Refrigerators not quite as much of an issue, you know, because those the load's a lot less, but also definitely things like air conditioners and the like. But yeah, it's just a little something for your consideration given the way the world's headed. And just as a repeat experiment, we'll see if we can get this thing to actually go out on the 1 kilowatt lamp. There we go. That killed it. Yeah, now at some point... Okay, the bimetal strip is still shunting out the starting electrode because these probe start metal halide lamps. Because of decomposition effects by having the starting electrode live at, you know, tens to, you know, 100 volts or so, with respect to the main electrode right next to it, metal halide lamps need a bimetal strip to short the two electrodes together to prevent this electrolytic decomposition. Now, as the lamp cooled down, okay, there's a little purple discharge. See a little bit of purple glow right at the bimetal strip. It's gone out. However, the arc tube pressure is still too high for there to be starting discharge. That momentary purple glow, that was just a discharge in the nitrogen gas fill of the outer envelope. Oh, here's a flash. There we go. Sparky, sparky. The color, it looks like that's mercury, because there's still going to be a bunch of mercury gas in the fill. By the way, for those of you who give a monkey's toss about this, this is a special kind of 150 watt metal halide lamp known as a ANSI type M107. Okay, now we've got discharge on both electrodes. And this is a reduced power replacement for a 175 watt M57 type metal halide lamp, assuming the ballast is rated for it, because not all ballasts are, because the way that these lamps work is the discharge is about a 1/4 inch shorter than in a standard 175 watt metal halide lamp. And so the arc potential is lower, and that's how it gets the power reduction, because it's running on close to the same current as a 175 watt lamp. However, this does mean that the ballast is being loaded a bit higher, so it needs to be designed for that higher loading. Okay, now we're getting the diffuse, and there we go. Lamp has restruck after about 4 minutes. And of course, obviously the ballast in this fixture is tri-rated for both of the aforementioned metal halide types, as well as an H39 175 watt high pressure mercury. See, there's the line of extension cords here. Carrying way over yonder. Here's the first. Or technically this is the third extension cord. That's the second one. And there's the electrical connection. Here it goes through more woods. Even more woods. And loads of bloody pricker bushes, which I need to get some goats to eat this garbage, plus get some meat and fertilizer out of the deal, as well as milk. More extension cord, which disappears into the grass, which I need to cut, because this extension cord's been out here since early this year, and this stuff has all grown up in the past couple of months. Another giant. That one's the first extension cord, that one's the second. And one trick is because of the size of this 18 gauge SJTW stock, not to be confused with SJWs, or scum of the earth, I'm using some electrical tape wrapped strain reliefs and wire expanders, so that way the crimps or the clamps on the plugs and receptacles don't crush the cords and grip them properly. And that's by using a different color for each extension cord. That's why that one's blue, that one's black, so I can tell which one is which. And some of the solar that's been feeding this, at least those 5. Because of course I'm running this experiment on solar. I'm me. Those 2 modules aren't hooked up at this time. Note, at this time. Extension cord. More extension cord. And here's the other end of the first extension cord, plugged into this combination 240 and 120 volt extension cord that I made. So these are NEMA 615 receptacles, and these are NEMA 515 receptacles. One receptacle on each of the 2 120 volt legs that constitute the 240 volts. And of course this is done the proper way, so there's a 4 conductor cable with a separate neutral and ground. By the way, this stuff is what is known as Arctic Flex. I actually got this from England, even though the cable's made in Turkey, by Savalkablo, so actually halfway decent stuff. It's comparable to our STTW cord stock, which is what these are made of, except it has the abominable European color code. And of course, this being 4 conductors meant for 3-phase applications, so green and yellow ground, and brown, black, and gray hots, although because gray is a standard neutral color over here for 277 480 and rarely 347 600, I'm just using the gray wire as a neutral. And there's the other end plugged into the L1450 receptacle on my Solarc main electrical panel.